So far in the blocks world, we have dealt with a one armed robot. That is how the strips domain was defined, that there are blocks on a table, the table is infinite, one block can only be can have only one other block on top of it, you can't have two blocks sitting on one block, and these kind of very simple qualitative descriptions. What if you were to deal with multi-armed robots or multiple robots? Can we adapt some of these planning techniques to that? So, let us have a quick look at that. This is more exploratory and it is not work which has been done a lot in the literature. Also, I have used various names here. I have said plan space planning, partial order planning, non-linear planning, least commitment planning. These are names which have been used in the literature for the same approach, which is we have called as plan space planning. Partial order planning, we understood that you impose order only on some actions in the final plan. Now, if it is a one armed robot, you can't help it, it can only do actions in a linear order. So, actions will have a total order which is a linear order, but in other domains, for example, if there are multi arm robots, then you can do things in parallel. One arm can pick up A, the other arm can pick up B, and both can be done in parallel. So, in that sense it is a partial order planning approach, it allows you to do that. It is non-linear also in the sense that it can produce plans which are not necessarily linear order. Least commitment is an interesting terminology, because it says that you do not commit to ordering the actions till you have to, essentially. So, in the last example that we saw, in this tiny example where you have to create on A B and on table B, we first found that 4 actions were necessary and we are not committed to putting an order onto that. But eventually we were forced to commit to imposing an order because of the fact that we had a one arm robo and all those threats were going to materialize otherwise, essentially. Now, let us look at how to handle the case of multi armed robots, essentially. So, we will begin with this thing. What if there is a 2 armed robot? Okay. So, this picture is the older picture in which there is only one armed robot, there is only one arm, as you can see, and this will lead to linear plans only, because that one arm can only do one thing at a time. It has only a linear sequential plan. We saw that in the previous example, it had 4, or in this example it had 4 time steps, essentially. What if we had a 2 armed robot? Just imagine that, and can we, so the second arm is now showing in the diagram. Can we find shorter plans? So, we are simply counting how many time steps you need to accomplish the plan. So, just look at this problem again, and now imagine that there is a 2 armed robot. It is like a robot with 2 hands, for example. Can it do faster than 4 time steps? So, what are the 4 time steps in the single armed robot? You pick up, you unstack B from C, that is the first action. The second action, put down B on the table. The third action is pick up A from the table, and the fourth action is stack A onto B, and it needed 4 time steps because there is only one arm. What if there were 2 arms? So, you can think that maybe some of those things can be done simultaneously. For example, one arm can unstack B from C, the other arm can pick up A at the same time, and they can be done in parallel. So, the total duration of the plan could become shorter, and let us investigate a little bit of that. So, the first exercise is to modify the strips operators to cater to a domain with a 2 armed robot. Let us start with that. And then you must ask the question that how can you have a general method which can be extended to multiple arms. But let us first tackle 2 arms, and so this is a problem given to us. There are 2 arms, let us just call them arm 1 and arm 2, and there is some planning problem that we are trying to solve, in which there are 2 columns, D is on A and C is on B, and we want D to be on top of C, but C should be on top of A, and we do not care where A is, essentially. So, the goal is described, as you can see, by 2 predicates, on CA and on TC, and now we want to see whether having 2 arms is a better, we can do it faster. essentially. If there was only one arm, you can see that you would have to, let us say, unstack D from A, keep it somewhere, let us say, on the table. Then you would have to unstack C from B and put it on A. So, that is 4 steps. Then you would have to pick up D and put it on top of C. So, that would be 6 steps. Can we do it in better than 6 steps if we have a robot with 2 arms essentially? So, first we want to modify the strips operators to work with those 2 arms, this thing, and then show that the plan when the plan space planning algorithm terminates essentially. So, these are the modified strips actions essentially. One thing that we will also address while we are doing this is this if the pickup and the unstack action. So, you pick up x from the table. When you picked it up, x was clear essentially. Should it be clear when you are holding it, or should it not be clear? Which means, should you delete clear x, or should you not delete clear x from the representation? Because if clear B is true, so if you look at this action stack A on B, you must be holding A, H stands for holding, and B must be clear, and then you say that B is no longer clear. But can we do something, do we need to do something similar when you pick up or unstack also? If you unstack a block, is it clear or is it not clear? So, we will look at that issue essentially. So, one way of working with a 2-armed robot is simply to have new actions. So, for example, stack 1. So, this is an error here, this should be stack 2. There are 2 actions, stack 1, stack 2. Stack 1 means it is an action done by arm 1, stack 2 means it is an action done by arm 2. Likewise, H1x means that arm 1 is holding this x, H2x means arm 2 is holding this x. So, this is one way of extending the solution. Similarly, for other operators essentially. Of course, this will not cater to, I mean, this will not scale up easily to multiple arms, because then you would have to keep adding actions for one particular arm essentially. So, this question that I was talking about, to delete or not to delete clear x when you are picking up x or when you are unstacking x essentially. So, this is our current operators, that you unstack A from B, as you can see on the top, and as a result B has become clear because you have taken B A from top of it, but we have not said anything about whether A is clear or whether A is not clear after that action. So, the alternative that I am talking about is that, remember that clear A is a precondition for unstack A from B. Should we delete it? Because very often for the other actions we have done that, right. We have said that arm empty was a precondition and arm empty is no longer true after the action. On AB was a precondition and not on AB is a effect. So, we have deleted arm empty and we have deleted. Why did we not delete clear A? The reason we did that in the one armed robot case is that if you unstack something, let us say A, or you pick it up from the table, the only thing you can do is either put it down or you can stack it onto something else, and at the end of that it will anyway be clear. So, why delete clear from this action? But now we are saying that what happens if we delete clear essentially, and you can see that the implication is that for multi-armed robots it may have an implication, and we will see that essentially. So, whether to delete that or not to delete that. So, in a one-arm robot case, the only thing that can happen is that you either stack it onto something or you put it down and then it will become clear. So, when you stack A onto B, if you are going to delete this, then you will need to add it again essentially. This thing. If you are not deleting it as shown on the right hand side, then you can see that clear A is not added as an effect of stack A. So, these are just two ways of looking at it. In the one armed robot, it does not matter whether you use the operators on the left hand side or on the right hand side, but we will see that in the case of a two armed robot, it does matter. So, we will come to that. So, this is the case that we are looking at it when we delete essentially. So, when we delete clear A, and the other change that we are making is that we are, instead of saying that there are two predicates holding 1 and holding 2, we are saying that there is an arm number n, and that n refers to which arm it is. So, it could be 1, 2, 3 depending on how many ever arms you have. So, AEN means the nth arm is empty. So, that small change we have added, and we have also added this case that when we delete that clear, which means that when you pick up A as shown here, an effect of that is A is no longer clear essentially. So, we are deleting clear A. It is also the case in unstack this thing. So, which means you have to add it when it is needed essentially. So, whatever I have drawn in this greenish thing is the change, that if you are going to delete clear A while pick up or unstack, then while stacking or putting it down you must add it to that, just to be consistent essentially. So, here is a solution plan essentially for this problem. Let us look at it in a little detail here. If you look at the actions as they happen in some order here, so there are two robot arms, remember. The first arm unstacks D from A and the other arm unstacks C from B. So, those two arms are picking up those two blocks D and C in parallel. Then we have this stack D on C. Why? Because that is a goal that we want to achieve, that D must be on C. And we have another action which is says stack C onto A, and that is because that is the other goal that we achieve. So, these two actions will come into the plan. The only question is when, can they be done in parallel or can they not be done in parallel. So, if you are going to delete that predicate which is shown in the green, that if you are unstacking D from A, you are deleting clear D, and likewise you are deleting clear C if you are unstacking C from top of B. Now, you can see that the stack this should be stack 2 because the second arm is stacking this thing. So, I have mixed up a little bit of this thing. So, you can only stack C onto D after you can only stack C onto A after C has become clear. So, what is happening? You have these two arms. One is holding D and the other is holding C. So, let us say this arrow stands for an arm essentially, and then your goal says that C should be on A and D should be on C essentially. You can put this onto A. So, this will go into C A, but stacking D onto C. Yeah, so this was correct. Arm 1 is going to stack D onto C. Stacking D onto C has to wait till C becomes clear. Because it is a precondition for this action, and this precondition is only achieved by doing this stack action. Then when you stack C onto A, initially we deleted clear C, then we are adding clear C. So, here we are adding it, and this is a causal link that we need essentially, that C must be clear, and only then you can stack something on top of T. So, you can see that this will be a 3-step plan, or 3 time steps will be required. One, in the first time step you unstack both the blocks, in the second time step you stack C onto A, and in the third time step you stack D onto C, and this is because of the way that we have represented this problem. So, this is again just the same thing in a simplified fashion. Oops. So, initially both unstack actions can be done in parallel, because we have these 2 arms which are doing this. So, unstack D from A using arm 1 and unstack C from B using arm 2. They can be done in parallel. Now, our unstack option has this delete option essentially. So, when we when we pick up or when we unstack, we delete the fact that clear. So, to unstack A from C, A needed to be clear, that is there, otherwise you can't pick it up. But in this version of our operators, we are also deleting it essentially. So, that is what we are using here when we delete clear A. So, when we do that, then we can obviously do stack C onto A. We are holding C and A is clear, because both this D and C have been picked up from this thing. What is the situation? The situation is A is on the table, B is on the table, and D is held by arm 1 and C is held by arm 2. After this first action, this is the situation. You are holding D and you are holding C essentially. So, clearly you can stack C onto A, because that is what you need to do. You put it onto C, and that is allowed by our actions. The other action, as we said, has to wait. Since clear C is not true, because we have deleted it, as you can see here, only stack CA can be done after clear A is true essentially, because this thing, which means after you have unstacked D from A, only then you can do stack C onto A. That is why this ordering link is here, this ordering link. So, that is why stack C onto A can happen only after the D has been unstacked essentially. And then of course, you can go ahead and stack D onto C after that situation, and you will achieve the goal. And as you can see, this has 3 time steps. This is the first time step, this is the second time step, and this is the third time step when the 3 actions happen. We sometimes use the phrase makespan to stand for how many time steps you need this thing, and the makespan of this plan is 3 essentially. Now, let us look at the case when we do not delete this essentially, which is what we have normally been doing. So, we say that whenever you pick up, let us say if the arm N picks up B, which means from the table, do not delete the fact that B is clear essentially. So, which means after pickup also B continues to be clear, clear B continues to be true essentially, whether it is pickup or whether it is unstack, it does not matter. N is the arm, and here you are unstacking B from C essentially, and you are saying that this is not the case, we are not doing this, and therefore, B continues to be clear in both these cases. So, since holding B and clear B are both true in either of these 2 cases, whether you are unstacking it from somewhere or whether you are picking it up from the table, you can see that holding NB is true and clear B is true. Why is clear B true? Because it was true to start with and we did not delete it essentially. So, this is true and this is also true. Now, if you look at this action of stacking something onto B, and let us say we are talking about different arm M, there are many arms here. You are holding B and according to the operators that we have defined, some other arm can bring A and stack it onto B, because the preconditions are true. What is the preconditions for stack MB? The preconditions for stacking MB is that you must be holding A and clear B must be true. These are the preconditions for the stack action. If you are holding a block A, I mean that of course M is simply the arm number. If you are holding the block A and if block B is clear, then you can stack it onto B. And here we have said that clear B is true, and if another arm has picked up A from somewhere, then holding A also would become true, which means both the preconditions are satisfied and this action can be done even while the first arm, which is N, is holding B in its hand essentially. So, if you think a little bit about this, you can see that there is some more parallelism that can happen, and we will come back to our example in this thing. This means that eventually a robot can end up holding a stack of blocks. It is holding B, for example, in this case, and then another arm has come and stacked A on top of B. Maybe a third arm will come and stack some D on top of A and so on. So, it can hold a stack of blocks, and that of course may affect the make span of our plans essentially. Now, if you were, so remember that you have picked up B, arm N has picked up B, so it is holding B, and you want to put it down, let us say on the table essentially. So, arm N can put it down onto B, and this stack M on top of A can happen at the same time essentially. There is nothing to say that these two actions cannot happen, can happen in parallel. So, if we try to imagine what is happening here is that one arm is holding B and the other arm is holding A. So, arm N is holding B and arm M is holding A essentially. So, in the same time step, arm N puts B down and arm M at the same time stacks it onto B essentially. So, in one time step both these actions can happen. This is because the way that we are defining our operators. Operators are applicable, you can apply them. As a small exercise, so you can see that if there were many arms, they could, and they were, supposing there were 5 arms and they were holding 5 blocks, in one time step they could construct a tower of 5 blocks essentially, because of the way this have been defined. So, as a small exercise, modify the domain so that you can only hold 2 blocks at a time. Now, remember that the strips world and even this modified strips world with multi-arm this thing, we do not have this luxury of using numbers. That will come if you were looking at metric domains. So, we said that PDDL 2.1 for example allows you metric domains. Here you do not have numbers essentially, you have only these predicates which can be either true or false. So, how would you contrive to represent a domain in which a robot can hold 2 blocks, but not 3 blocks or 4 blocks? It can be done, it needs a bit of a thought. So, let us come back to our example. This is our starting state on the top left. D is on A and C is on B, and we have 2 arms available to us, and we want D to be on C and C to be on A essentially, and we are doing plan space planning. Both the unstack actions as before can be done in parallel. That could be done even when we were deleting that predicate. Now, unstack n x, this is a situation when you are unstacking x from y, this action now does not delete x, it continues to be clear essentially. So, in both these cases, in the left hand action D continues to be clear, in the right hand action C continues to be clear. They were clear to begin with, and what we are saying is that even if you have picked it up, they are still clear essentially. Now, since clear C in particular, we are interested in clear C because we want to stack D onto C. Remember, this is an action we want to do, which is to stack D onto C. Since clear C remains to be true, what are the conditions you need for arm 2 to stack C onto A or D onto C? This action, what are the preconditions for this? The preconditions are that arm 1 is holding D and C is clear. These are the only two preconditions you need for stack 1, which means arm 1, for arm 1 to stack D onto C. It must be holding D and C must be clear essentially. Now, you can see that when it unstacks, when it had unstacked D, this condition was satisfied. This was an effect of that, and this clear C was true in the beginning and it has not been deleted. That's what our way of representing this thing. So, both these preconditions are met, and in the next time step D can stack it onto C. In the same time step C can also stack it onto A because of these preconditions are satisfied, and this ordering link that we had earlier does not exist anymore because of the way that we have defined our operators. And you can see that this happens in two time steps. In the first time step, the two robot arms unstack D and C respectively. Then in one step, D is stacked onto C and C is stacked onto A. A is on the table, if you remember, and we have a shorter plan. Here is another example of a partial plan. So, we are talking about, suddenly we have started talking about parallel plans which can be executed in parallels essentially. So, let us say that you are in the process of getting ready to go to college or going to office or something like that, and let us say this is your plan every day in the morning, that you wear your clothes, then you comb your hair, then you wear your left sock, and after wearing the left sock you can wear the left shoe, and likewise you wear your right sock, and after wearing the right sock you can wear the right shoe, and they have to be done in order. So, you have to first wear the sock and then only you can wear the shoe essentially, but there is no order specified here. Supposing you were to do this as a sequential plan, what is the plan that you can produce? So, as you can see, actions 2 and 4, wearing the socks, can be done in parallel. If you are dexterous enough, then with both hands you can wear both your socks, and then with both hands you can wear both your shoes, and they can be done in parallel. But if you want a linear plan, then any topological sort of this partial order is a valid linear plan as well. So, what is a topological sort? A topological sort says produce a linear order, but it must respect these red arrows that we have drawn, that action A must come before 4, action 1 must come before 2, and so on and so forth. So, you can see that action 1 is always coming first here, but then if you are doing plans in a linear order, you can first say the second action is to wear the left sock, and that is shown here. The other option is to wear the right sock, which is shown in the bottom 3. After wearing the left sock, you still have the freedom. I think you can either wear the left shoe or you can wear the right sock, after which again you have a little bit of freedom as to in which order. So, basically there are these different orders which are consistent with the partial plan. The partial plan you can imagine as a plan which can be executed in parallel, and you can also linearize it in many different ways in any order, and any of them would be a valid plan essentially. Let us just do a bit of a recap on this. A plan is a set of actions designed to transform the given state into a desired or a goal state when executed. So far we had said that a plan is a sequence of actions, and suddenly we are now saying that plans can happen in parallel. So far we said plan is a sequence A1, A2 up to AN essentially, but actions can now with this partial order planning can happen in parallel, and there is going to be a difficulty if actions had durations. Then what does parallelism mean essentially? Because can two actions be done in parallel with a third action? So while your water is boiling, you chop the, let's say, bhindi and you chop the tomatoes one after the other, and can this whole thing be done in parallel? So when actions have durations, there is more complication. In forward state space planning, the first action selected is the first one scheduled. So there is a tie up of when you select the action and where you schedule it. In backward state space planning, the first action selected is the last one to be scheduled, because it always picks the last action first. In goal stack planning, the first action that is proposed is the last one to be scheduled essentially. And what we have shown that in PSP there is a possibility of separating the task of selecting actions from scheduling them. So we simply say this action must be selected because it is satisfying some open goals. The ordering can come later essentially, and we have seen that we can have plans which can be executed in parallel. So this question of how selecting an action for a plan and scheduling it, we will come back to this question a little bit later exactly.